Verilog, standardized as IEE 1364, operates as a hardware description language, HDL, utilized for the modeling of electronic systems, commonly in designing and validating digital circuits with the primary focus on the register transfer level of abstraction. It finds application in verifying analog circuits, mixed signal circuits, and genetic circuits. In 2009, the Verilog standard, under IEE 1364-2005, got merged into the System Verilog standard, establishing IEE standard 1800-2009, subsequently making Verilog an integral part of the System Verilog language. Presently, it aligns with the IEE standard 1800-2023. Hardware description languages like Verilog share similarities with software programming languages by specifying propagation time and signal strengths. Verilog incorporates two assignment operators, a blocking assignment, equal sign, and a non-blocking, less than equal assignment that aids in describing state machine updates without necessitating temporary storage variables. Verilog's language semantics empower designers to succinctly describe extensive circuits. Upon its inception in 1984, Verilog immensely boosted productivity for circuit designers who were transitioning from graphical schematic capture software and custom-written software programs for circuit simulation documentation. The language was patterned with a syntax akin to the prevalent C programming language to facilitate engineers already accustomed to engineering software development with C. Verilog is case-sensitive, integrating basic preprocessor features similar to ANSI C and C++, with control flow keywords, operator precedence, and syntactic variations unique to Verilog's design requirements. Variable declarations in Verilog mandate explicit bit-width specifications compared to C's inferred sizing based on variable type. A Verilog design comprises modules organized in a hierarchy. Modules encapsulate design hierarchies and interconnect with other modules through specified input, output, and bidirectional ports. Internally, a module may encompass net variable declarations, concurrent and sequential statement blocks, and instances of other modules, formulating subhierarchies. Sequential statements housed within begin-end blocks execute sequentially within the block, albeit the blocks function concurrently, rendering Verilog a data flow language. Verilog's wire concept encompasses four state signal values, 1, 0, floating, undefined, and signal strengths, strong, weak, etc., enabling abstract representation of shared signal lines where multiple sources steer a common net. Synthesizable Verilog statements construct Verilog modules conforming to the register transfer level, RTL style, capable of physical realization by synthesis software. This software algorithmically transforms abstract Verilog source code into a netlist comprising elemental logic primitives, and, or, not, flip-flops, etc., thereby enabling the fabrication of circuits specific to FPGA or VLSI technology, ultimately leading to the production of circuit blueprints. Verilog emerged in the early 1980s, crafted by Prabhu Goel, Phil Morby, and Qilai Huang. The latter had prior experience with the LALSD hardware description language during his doctoral studies under Professor S.Y.H. Su. Initially a proprietary technology controlled by Automated Integrated Design Systems, which later rebranded as Gateway Design Automation, Verilog found broader adoption once Cadence Design Systems acquired Gateway in 1990. With Cadence's ownership, Verilog and its HDL simulator, Verilog XL, rose to prominence as the industry standard throughout the 1990s. The term Verilog itself is a fusion of verification and logic. As VHDL gained traction, Cadence opted to open up Verilog for standardization. Consequently, the language transitioned to public ownership under Open Verilog International, now recognized as Accelera. This shift culminated in Verilog's formal acceptance as IEE Standard 1364-1995, commonly referred to as Verilog 95. Concurrently, the inception of Verilog A aimed to bolster standards for Cadence's analog simulator, Spectre. Verilog A, a subset of Verilog AMS which enveloped Verilog 95, catered to analog applications. Addressing user feedback, enhancements to Verilog 95 were proposed, leading to IEE Standard 1364-2001, known as Verilog 2001, an appreciable advancement over its predecessor. Noteworthy additions included explicit support for signed nets and variables, simplifying complex operations and bolstering code readability. Moreover, Verilog 2001 introduced a generate-end-generate construct, akin to VHDL, enhancing instance and statement instantiation flexibility. Verilog 2005, distinct from System Verilog, delivered minor fixes, specification clarifications, and a handful of fresh elements like the UWire keyword. Meanwhile, Verilog AMS sought to merge analog and mixed signal modeling with traditional Verilog, paving the way for System Verilog's creation. Boasting enhanced capabilities for design verification and modeling, System Verilog, an outgrowth of Verilog 2005, superseded its predecessor. By 2009, both System Verilog and Verilog standards coalesced under System Verilog 2009, I Standard 1800-2009, unifying their directives. Over subsequent years, the System Verilog standard underwent timely revisions in 2012, 2017, and most recently in December 2023, ensuring the language's relevance and adaptability in the evolving landscape of electronic design automation. The Verilog code snippet provided showcases the use of non-blocking and blocking assignments in hardware description languages. In the example of two flip-flops, the Nebuchadnezzar operator indicates a non-blocking assignment where values are updated after the block execution, ensuring that flop 1 and flop 2 swap values effectively every clock cycle. Conversely, the equals operator represents a blocking assignment, updating the target variable immediately. By employing non-blocking assignments, the order of operations becomes irrelevant, highlighting a key distinction from traditional procedural languages. Furthermore, the counter-circuit example demonstrates the practical application of these assignment operators in a divide-by-20 counter with clock enables. The module utilizes parameters and input signals like RST, CLK, CET, and CEP to manipulate the count value and generate the TC output. The always block, triggered by clock or reset transitions, showcases the reset functionality and count increment based on enable conditions, ultimately illustrating the significance of different assignment operators in Verilog. Additionally, an example featuring delays exhibits how signals A, B, C, and D are manipulated within an always block based on changes in inputs B and E. The use of blocking and non-blocking assignments with time delays underscores the nuanced behavior of Verilog in updating signal values over time. Notably, signals driven internally within a process are declared as regi, while those external are declared as wire, emphasizing a crucial distinction in signal handling within hardware description languages. The Verilog language allows for defining constants with a specified width parameter indicated by a number and then a single quote. After the quote, a base letter is used followed by the number. For instance, examples include 12 single quote H123 for a 12-bit hexadecimal number, 123, 20 single quote D44 for a 20-bit decimal number 44, which is automatically 0 extended, 4 single quote B1010 for a 4-bit binary number 1010, and 6 single quote O77 for a 6-bit octal number 77. While some Verilog statements like the $ display command lack hardware equivalents, others directly map to real gates. For example, multiplexers can be implemented using continuous assignments, procedural assignments, or if/else constructs. Another important structure is the transparent latch, which forwards inputs when the gate signal is active and captures the input upon signal transition for storage. A flip-flop, specifically the D-flop, is a fundamental Verilog element utilizing non-blocking assignments during clock edges. Variants include the D-flop with asynchronous reset and both asynchronous set and reset conditions. Model shortcomings can emerge during simulations if not properly accounted for, as shown in the example of a set-reset flip-flop sequence of events. Handling reset and set conditions correctly is crucial. An additional variant integrates a mux feeding input to a D-flop, offering a gated load capability. Notably, FPGA and ASIC synthesis tools approach initial states differently, with FPGA tools allowing for initial blocks, while ASIC tools do not support this feature due to the distinction in hardware implementation. There are two distinct methods for declaring a Verilog process, utilizing the always and initial keywords. The always keyword signifies a continuous process, running perpetually. On the other hand, the initial keyword denotes a process that executes precisely once. Both mechanisms commence execution at simulator time 0 and persist until the conclusion of the block. It is essential to note that contrary to popular belief, an initial block does not necessarily execute prior to an always block. Instead, it is more accurate to consider the initial block as a specialized version of the always block, which ceases operation after its initial run. An example of an initial block includes assigning a value to a register A at time 0, followed by a wait of 1 time unit, and then assigning the value of A to another register B. In contrast, an illustration of an always block involves a process triggered by a change in either A or B, where EC or D is assigned a value based on certain conditions, denoted by logical operations. Moreover, both constructs can be utilized without a sensitivity list, as demonstrated by an always block that executes continuously without specific triggering conditions. Furthermore, there exists a notable utilization of the initial keyword combined with the forever keyword. This amalgamation mirrors the perpetual execution characteristic of the always keyword, exemplified by a continuous operation where a clock signal alternates between 0 and 1 with specified time delays between transitions. The convergence of these keywords showcases the flexibility and diverse applications of Verilog processes in digital design. Verilog utilizes a fork-join pair to establish parallel processes. All statements or blocks enclosed within a fork-join pair commence execution simultaneously when the fork is reached in the execution flow. Upon the completion of the longest running statement or block within the fork or join pair, the execution progresses after the join. The sequence ABC or BAC may be printed due to the non-deterministic behavior of the simulator, varying based on the simulator's implementation, potentially introducing randomization intentionally. Unlike Verilog, VHDL lacks the capability to dynamically generate multiple processes. In Verilog, the execution order is not guaranteed, which can lead to race conditions. A simple illustration of this uncertainty is exemplified in a code snippet where the values of variables can either both be 0 or 0 and an uninitialized value, depending on the order of execution of the initial blocks. The $sign display statement unfailingly executes after the completion of both assignment blocks due to the number 1 delay. The operators used in digital design include bitwise operators like AND, OR, and NOT, along with XOR and XNOR. These operators manipulate binary values. Additionally, there are arithmetic operators such as addition, subtraction, multiplication, division, and exponentiation. Logical operators such as greater than, less than, equal to, and not equal to are used for making comparisons between values. Shift operators, which include both logical and arithmetic types, are employed to shift the bits of a binary number to the left or to the right. Concatenation operators, denoted by curly braces, combine multiple values into a single entity. Replication uses the format curly brace n curly brace m close curly brace to duplicate a value m for n times. Conditional operators like the question mark enable the implementation of conditional statements. In terms of multi-valued logic, E3064 standardizes a 4-valued logic system with states 0, 1, Z, high impedance, and X, unknown logic value, whereas VHDL employs IE 1164 with 9 levels to handle multi-valued logic. The system tasks within Verilog are essential for handling simple I/O operations and various design measurement functions during simulation. These tasks are prefixed with a $sign to differentiate them from user tasks and functions. While not an exhaustive list, some of the most commonly used system tasks include $sign display for printing a line to the screen with an automatic new line, $sign write for printing a line to the screen without a new line, and $sign fopen for opening a handle to a file for reading or writing purposes. Additionally, tasks like $sign readmem and $sign readmem are used to read content from hex and binary files into a memory array, respectively. Another crucial system task is $sign time, which provides the current simulation time value. Furthermore, the Program Language Interface, PLI, acts as a bridge between Verilog and C programming languages, allowing for seamless transfer of control from Verilog to C functions. The PLI, now known as VPI, facilitates collaboration between Verilog and other C-based programs such as test harnesses, debuggers, and instruction set simulators for microcontrollers. This interface introduces functions like tf-put-long-p and tff-get-long-p for handling 64-bit integer arguments in Verilog tasks or functions, while tff-put-get-puts and tff-get-put beyond it cater to 32-bit integers. EASE 364-2005 has deprecated the PLI in favor of the Verilog procedural interface for enhanced functionality and compatibility within the programming environment.